Hello everyone! This video is entitled Quantum Numbers. Quantum numbers are a set of 4 numbers that describe the unique characteristics and properties of electrons in an atom. These numbers help us to identify the energy, position, and orbital shape of electrons within an atom. In this video, I will work through a detailed example of the application of these 4 quantum numbers for a rather large ion. If you would like to learn more about how quantum numbers explain the structure of the periodic table and the behavior of matter at an atomic level, I recommend that you watch my video entitled Quantum Theory. You can find a link to that video in the description below. Okay, let's get started. I'm choosing a lengthy example here so you can use it as reference when studying for a quiz, a test, or answering questions. The example I'm choosing is the selenium ion. Now, based on its position on the periodic table, it has 34 electrons. That means that you have to write out 34 separate lines for each electron, each line with the 4 quantum numbers for each electron. But in fact, because I've picked the ion here, we're not actually doing 34 electrons. We're doing 36. What we're actually doing is writing out the quantum numbers that are equivalent to krypton. Before we begin, I would like to draw your attention to the atomic number of each element. At the end of every line that I complete, I'll be writing the symbol of an element. This is because at the end of the first line of quantum numbers, I would have written those equivalent to hydrogen. At the end of the second line, those equivalent to helium. At the end of the 24th line, those equivalent to chromium, and so on and so forth. This example is a great reference because it clearly outlines the quantum numbers of every element leading up to krypton. At the start of any example, it is important to remember that the orbitals in the lowest energy level must receive electrons first and become filled before you can move on to the orbitals in the highest energy level. It begs to reason that we would start with energy level 1 because the s orbital in that energy level is closest to the nucleus. So we start by writing n equals 1. Now if n equals 1, L must equal 0. And that's because of the limits that n equals 1 places on L. If L is equal to 0, then ML must also be equal to 0. So what I'm going to do now is I'm going to place an electron into this s orbital by writing ms positive 1/2. So that's the positive spin electron. What I've written now are the quantum numbers equivalent to that of hydrogen. I'm going to place a second electron in this s orbital by writing ml equals 0 and ms equals negative 1/2, the negative spin electron. Now I have quantum numbers equivalent to those of helium. I've now filled the first orbital, and really the only orbital in the first energy level. Now I can move on to the second energy level. Before I do, you'll notice that I didn't write n equals 1 and L equals 0 for the second line, because it's redundant. As long as I write the ML and MS of every single line, I've essentially accomplished what I need to accomplish. The only time I need to write the first 2 quantum numbers is when I'm moving on to a new energy level, okay? Or I'm moving on to a new orbital type. So now I'm going to move on to the second energy level, n equals 2. The second energy level has 2 types of orbitals. It has an s orbital and it has 3 p orbitals. Now before I fill the p orbitals, I need to fill the s orbital. And this is denoted by the value of L. So if L is equal to 0 for s and L is equal to 1 for p, it only makes sense to start with the lower value first, to fill that lower value, hence why they gave it a lower number. And so I'm going to write L equals 0 and start with the s orbital for the second energy level. Its ML will again be 0, and I'll place a positive 1/2 electron. Now I have the quantum numbers for lithium. The second electron will now be a negative half, and this is beryllium. Now I've filled the s orbital in the second energy level, and I'm now going to move on to the p orbitals. I do this by writing L equals 1. Now you have to remember that for L equals 1, ML ranges from -1 to +1. And so I start with the lower integer, -1. And so ML will be -1. I'm going to put my first electron in that orbital. Now I have boron. And many would think, okay, well now I'm going to fill the -1 orbital with a -½ spin electron. So you're thinking, let's just fill that orbital. In fact, that's not what we're supposed to do, and the reason being is because of Hund's rule. Remember, Hund said that we need to fill each one of the p orbitals with 1 electron first before we move on to the second electron, before we pair it with the opposite spin. What's more is each electron that we place into a p orbital must have the same spin. And so what I should be doing now is ML equals 0. So that's the second p orbital. And I'm going to place, again, a +1/2 spin electron. Okay? Now I have carbon. I'm going to place the next electron into the ML +1. Okay? This is the third p orbital. And it is another 1/2 spin electron. I have nitrogen now. Now that I've filled each one of the p orbitals with 1 electron, I'm now going to pair each single p orbital with an opposite spin electron. And so I'm going to start again now with the -1 ML. And add, as you can see here, a -1/2 electron. Now I have oxygen. Keep in mind, what I have written here, this whole series, would be the quantum numbers that I would need to write to get to oxygen. So if I just asked you a question, what are the quantum numbers for oxygen, it would be what you see before you write now. Okay, you'd have to write the whole series. You can't just write that one line for oxygen. So when you see these elements symbolized on the right here, you can't just write that one line. You need to write all of these quantum numbers to arrive at that one element. And I'm now going to continue with ML equals 0 and MS -1/2. I now have fluorine and the last p orbital, and I have neon. At this point, we've concluded with the second energy level. Now we need to move on to the third energy level. So N equals 3. Remember, we're done with the second energy level because we've filled the s orbital and we've filled the p orbitals. Okay, what you can see here is I've half filled the first 3 and I've paired them again with their negative spin. The third energy level is a little bit different from the second one in the sense that it has 3 types of orbitals. It has the s orbital, it has the 3p orbitals, and it has 5d orbitals. Okay, and so it gets a little tricky when we're doing the third energy level, but we're going to start the exact same way, just like we started with the second energy level. We're going to start with the s orbital. And so I'm going to write L equals 0, ML equals 0. I'm going to put the first electron in. I have sodium now. The second electron, I have magnesium. Now that I've filled the s orbital, I'm going to go on to the p orbitals. So -1/2, its electron. Remember, it's going to be all positive spin for the first 3. So I have aluminum, positive spin. I have silicon, positive spin. I have phosphorus. I've now half filled the p orbitals for L equals 1. Now I'm going to pair it with the opposite spin. Okay, so sulfur, chlorine, and argon. So now at this point, I've filled all of the p orbitals for the third energy level. Okay, now at this point, it would only make sense to move on to the d orbitals that are now in the third energy level. But in fact, if you look at the periodic table, the d orbitals don't come first. It's the s orbitals for the fourth energy level that come before the d orbitals of the third energy level. Let me show you what this looks like on the periodic table. This image here shows the relationship between the periodic table and the orbital sublevels. As you can see, in group 1 and 2, you'll have the s orbitals, with one exception, helium, located over here in group 18. And you have all of the p orbitals located between group 13 and 18. The d orbitals are the transition metals between group 3 and 12. And interestingly enough, you have the f orbitals sandwiched in between the d block and the s block. And again, that's what we call it. We call this the d block, and we call this the s block. We call this the p block. And this, of course, would be the f block. And so we have the f block sandwiched in between the d block and the s block in periods 6 and 7. Now, I'm going to explain a little bit more about the f orbitals in the next lecture. But for now, we just finished filling the orbitals up to argon, which is this element right there. And so we need to now fill the d orbitals. But before we can fill the d orbitals, these d orbitals here, to get to krypton, which is located right here, we actually need to fill these two s orbitals, elements 19 and 20, potassium and calcium. And the reason being, if you look again, we finished filling argon at the end of the 3p block. But before we can get to the d block, we need to fill this s orbital in the 4th energy level. And so that's why we actually have to jump from the 3p to the 4s before we can get to the 3d. So going back to our example, we've just written all of the quantum numbers for the elements leading up to argon. And we just finished filling the p orbitals in the 3rd energy level. But as I just showed you, we need to go from the 3rd p orbitals to the s orbital in the 4th energy level before we can get to the d orbitals in the 3rd energy level. And so to do that, we need to write n equals 4. And of course, we denote the s orbital in the 4th energy level by writing L equals 0. Ml is of course equal to 0. And you have the first spin electron, the positive spin electron. That will be potassium. The second spin electron will be calcium. Now that we've filled the s orbital in the 4th energy level, we can now jump to the d orbitals for the 3rd energy level. We've now arrived at the 3d orbitals. And as always, we're going to start by writing the energy level, n equals 3. In this situation, L will be equal to 2. We don't have to worry about L equals 0 or L equals 1 anymore, because we've already filled those orbitals. So we can jump directly to L equals 2. As always, ML ranges from negative L to positive L. And so in this situation, our ML will be negative 2. I'm going to place an electron in this orbital with a positive spin, and that gives me the quantum numbers for scandium. Now, please bear in mind that Hund's rule applies to d orbitals just as it applies to any other orbitals. So as you saw with the p orbitals in the last slide, we need to fill each one of the d orbitals with positive spin electrons. We must half fill those orbitals first with positive spin electrons before we can then go back and double up with an opposite spin electron. And so instead of writing another line for negative 2, I'm going to write the next line as negative 1. So I'm jumping directly to the next d orbital. Again, I'm going to give it a positive spin electron, as all the half-filled orbitals must be filled first with a positive spin electron. That gives me titanium. The next orbital will be 0, positive spin electron, vanadium. And now I'm going into positive 1, positive spin, chromium. Positive 2. So this is the end of my range for the d orbitals. Positive spin, and manganese. So now that I've filled my d orbitals with a positive electron, I'm now going to double up those d orbitals with a negative spin electron. So I'm going back now to -2. I'm going to place a negative spin electron, and I get iron. -1, cobalt. 0, nickel, and +1, copper, and +2, zinc. And so by doing what I've just done, I've half-filled the d orbitals first with positive spin, and now I've filled the d orbitals by pairing up those half-filled electrons with a negative spin. And so now I've completed my d orbitals for the third energy level. And so before I move on, you need to now bear in mind we've jumped now from the 3d to the 4p. If we go back to the periodic table, I can show you what that looks like. So we've just finished writing the quantum numbers for the elements in this highlighted area here. The last element we wrote a line of quantum numbers for is zinc, right there. Now you can see, after the d orbitals, we now move into the 4p orbitals. And so we now have to jump again. We jump from the third energy level back to the fourth energy level. And so we've done this now twice. We've jumped from the 3p to the 4s, and then from the 4s to the 3d, and now we're going to jump back to the 4p. Here we have the completed d orbitals for the third energy level. Now I'm going to jump back to the fourth energy level to complete the p orbitals. So to do this, I of course have to write the energy level, n equals 4. Now I've already completed the s orbital for the fourth energy level, L equals 0, and so now I can jump directly to L equals 1 for the p orbitals, so L equals 1. Remember that ML ranges from -L to +L, and so I'm going to start with -1. I'm going to half fill this orbital with a positive spin electron, and I have gallium. Now, as always, I'm going to half fill each one of the p orbitals first with a positive spin. So I'm going to go to the next orbital, which is 0, positive spin, germanium. And then the next orbital will be +1, positive spin, arsenic. And now that I've half filled my 3p orbitals, I'm now going to fill them by pairing them with a negative spin electron. So going to my -1 again, negative spin electron, I'm now at selenium. Now, some of you are thinking, oh, we're done. We're at selenium. Well, actually, I've picked out the selenium ion as my example. And so you can see that the selenium ion is 2 negative, meaning what I've done is I've added 2 more electrons to selenium. So if you follow that to conclusion, in fact, I'm not stopping at selenium, I'm stopping at the quantum numbers that are equivalent to krypton. And so the next electron I need to add will give me bromine. And finally, I'm now filling my 4p orbitals with the last negative spin electron, and that gives me krypton. And this would be the completed set of quantum numbers for the question of the selenium ion. So I hope this example has clarified things for you. I hope it shows you how these quantum numbers work in relation to each other. And I also hope that you can use it as reference for future questions and homework that you may use as practice. This slide and the next slide are essentially review slides. They provide charts that organize all of the information that we've discussed in this package. They show you all of the sublevels and all of their respective quantum numbers to the maximum values that you can have for each quantum number. This table is a little bit more streamlined. Essentially, it shows the maximum number of electrons you can have in each sublevel, or the maximum number of electrons you can have in any one energy level. Okay, guys, so I hope you enjoyed this package. I hope you understood this lecture. It was a pleasure. All the best.